Hello everyone. Today I will share with you a project I've been working on for a while, which is a PBR renderer. I will delve deep into the theoretical parts of most aspects required to create a PBR renderer. Well, PBR, or physically based rendering, is a collection of techniques that tries to mimic real-life light in a physically plausible way. To understand the physically based rendering theory, we first need to understand how light works. In real life, light exits from a point light source in all directions. When a ray of light hits a surface, the surface absorbs some wavelength of light and reflects others, which is what determines the color we perceive. The reflected light then scatters in various directions. Many of these rays are lost in the space, and only a small portion reaches our eyes, allowing us to see the surface. And since we are working in real time, we are limited by the hardware capabilities, so most of the time we will be doing approximations and assumptions. That's why we call it physically based rendering and not physically rendering. Every PBR model must follow these two principles. The first one is the microfacet surface model, and the second one is the law of energy conservation. For the microfacet surface model, the theory suggests that at a microscopic level, any surface can be thought of as tiny, perfectly reflective mirrors, called microfacets. On rougher surfaces, these microfacets are aligned more chaotically. The microfacets are small enough that we cannot differentiate them on a pixel-by-pixel basis. Instead, we use a roughness parameter that ranges from 0 to 1 to statistically estimate alignment and roughness of the microfacets. For the law of energy conservation, this one states that the resulted outgoing light energy should never exceed the incoming light energy, of course excluding emissive surfaces. This makes the assumption that all refracted light gets absorbed and scattered directly after the impact with the surface, ignoring all the subsurface scattering. In 1986, some smart dudes named David Immel and James Kajiya introduced an equation we now call the rendering equation. Every PBR model is an attempt to solve this equation. Well, don't be scared by these fancy integrals, because all what it says is that the outgoing light at any given point x is equal to the reflected light plus the emitted light. To deeply understand this equation, we will try to build it bit by bit. Since the emitted light does not affect the law of energy conservation, we can remove it for now and add it back later when we finish building the equation. So the equation will be the outgoing light equal to the reflected light. If we imagine a scene with a directional light and a sphere and make simple assumption that the outgoing light equal to the incoming light, then the output will be like this. But in real life, faces with normals that points away from the light source are darker than the faces that points directly to the light. To model this, we can use a mathematical operator called the dot product, which returns 1 when the angle between two normalized vectors is 0 and 0 when the angle is 90. By doing the dot product between the incoming light direction and the normal of the surface, we got a flipped result of what we want. We can fix this by flipping the direction of the incoming light. But this model accounts only for one single directional light. If we want to add multiple lights, we have to calculate every possible incoming light direction in the surrounding hemisphere. In math, we can model this using an infinite integral. But since it's infinite, we cannot calculate it in real time. We usually know the exact number of light sources and their direction. So this integral will be the sum of the incoming light directions. Or in some cases like image-based lighting and path tracing, we will be approximating the solution of this integral using methods like the Monte Carlo method. But this model assumes that all light rays get absorbed and scattered with the same amount, which is not what happens in real life. To model this, we will use an abstract approach and replace the one with a function. This function is called the bidirectional reflectance distribution function, in short, the BRDF. The bidirectional reflectance distribution function is a function that takes as input the incoming light direction and the outgoing light direction, which is equal to the view direction, and some of the surface properties like the normal and the roughness, and outputs an approximation to the contribution of every incoming light to the final outgoing light. Using RGB values ranged between 0 and 1 to represent the diffuse color of the surface, we can write the simplest BRDF, which is the Lambertian diffuse, named after Johann Heinrich Lambert, who introduced the concept of perfect diffusion in his 1760 book Photometria. This BRDF function is equal only to the diffuse color of the surface divided by pi, which means that it's independent from the incoming light and outgoing light. Although this BRDF is great, but it does not allow us to represent shiny surfaces like polished metals. In real life, when a light ray hits a surface and gets absorbed, it scatters in all directions, which represent the diffuse light. But not all of it gets scattered in all directions. A certain amount of it will be directly reflected, which we refer to as the specular reflection. This reflection happens on a small range that depends on the view direction. We call it the specular lobe. So in 1975, at the University of Utah, Bui Tong Fong published in his PhD the Fong BRDF. The Fong model splits our BRDF function to two other BRDF functions. A diffuse BRDF represents the Lambertian diffuse, and a specular BRDF that models the specular highlights using the dot product between the view vector and the reflected light vector. This means that the smaller the angle between these two directions, the stronger the specular highlight will be. A shininess parameter is used to control the strength and sharpness of the specular highlight, with higher shininess values producing a more focused and intense highlighting, and lower values result in a broader and softer result. And since the normal vector is the halfway vector between the reflected vector and the incoming light vector, we can calculate the halfway vector between the view direction and the incoming light vector, and then calculate the dot product between the normal vector and the halfway vector to get the amount of the specular highlight. This optimization was introduced by Jim Blinn in 1977, which gave us the most used lighting model in games and CG with the name of the Blinn-Fong model. Although the Blinn-Fong can model almost any surface with a good looking result, it does not follow the law of energy conservation, which makes it considered as a not physically based model. Nowadays, there are several physically based BRDFs out there, but almost any real-time PBR model uses a BRDF known as the Cook-Torrance BRDF, which was introduced in a paper by Robert Cook and Kenneth Torrance in 1981. In my project, I integrated Disney's implementation of the Cook-Torrance BRDF, which was adopted by Epic Games in their Unreal Engine 4. This BRDF function looks like this, where KD is the amount of incoming radiance that get diffused, and Ks is the amount of light that is peculiarly reflected. And since we are following the law of energy conservation, Kd plus Ks must be equal to 1. In this equation, Ks is equal to the Fresnel factor and Kd is equal to 1 minus Ks. The Fresnel factor describes the ratio of light that gets reflected. The lower the viewing angle is, the more the reflection is. And it's represented by the Fresnel-Schlick equation, which is an approximation to the actual Fresnel equation, where f0 represents the base reflectivity of the surface, v is the viewing angle, and h is the halfway vector between the viewing angle and the incoming light vector. For the f diffuse, we replace it with a Lambertian diffuse. The specular part of the BRDF is a bit more complicated, and it's described by this equation, where d is the normal distribution function, g is the geometry function, f is the Fresnel equation. And since the Fresnel equation is present in the Cook-Torrance specular function, we have to remove the Ks, otherwise we are applying the Fresnel effect 2 times. The normal distribution function approximates the alignment of the microfacets to the halfway vector h. There are several normal distribution functions out there, but the more common one is the Trowbridge-Ritz GGX, which is represented by this equation, where n is the normal of the surface, h is the halfway vector, and a is the roughness. The Fresnel equation describes the ratio of the surface reflectivity at different surface angles, as described before. The geometry function statistically approximates the relative surface area where its microfacet surface details overshadow each other. In my project, I used the Smith method to take account of both the view direction and the light direction vector. This method multiplies between two subgeometry functions. The first one takes as input the normal and the view vector and a k property, and the second one takes the normal of the surface, the light direction, and a k property, where k is equal to the roughness plus 1 to the power of 2 divided by 8 in case of direct lighting, but in case of image-based lighting, k will be equal to the roughness of the surface to the power of 2 divided by 2. In my project, I used the Schlick GGX function for the geometry subfunctions, which is a combination between the GGX and the Schlick-Beckman approximation. The geometry function then returns a value between 0 and 1, with 1 when there is no microfacet shadowing, and 0 when there is a complete microfacet shadowing. Assembling all of this together, we get the final Cook-Torrance reflectance equation. With this equation and properties based on physics, we can model any surface and achieve more physically plausible results. You will find the references and the GitHub repository for the project in the description below. Thank you for watching, and don't forget, always look around, you will find a Fresnel effect.